Hi, my name is Jazz Munitz and I'm a senior at Hendrick Hudson High School in Montrose, New York. And today we're at the Icahn School of Medicine at Mount Sinai Translational and Molecular Imaging Institute's Nanomedicine lab, where I've been conducting research for the past 3 years alongside the brilliant scientists who work here. Today I'd like to give you a brief overview of my research, the microfluidics facilitated synthesis and characterization of low-cost nanoparticles for cancer therapeutics. And while that's a long and complex title, let's break it down. Alright, so microfluidics facilitated synthesis. So essentially what this means is that I'm using a new and unique approach to synthesizing nanoparticles, and it's a technique which you might have heard about in a technology kind of considered lab on chips currently. Essentially it's using these very small nano or micro reservoirs as well as small little tubes connecting them in order to create microvortexes and synthesize nanoparticles. So characterization. So while we're in a lab setting, we want to make sure that we can learn as much about the nanoparticles, their structure, their shape, the ways in which they interact, so that once we put them into an in vivo model, we know as much about them as possible, which will make it easy to manipulate and to learn. Apoptosis inducing. That means that once it's able to reach the cancer cell, we want to make sure that it has the ability to kill cancer. Low-cost nanoparticles, so it's really more cost-effective in that we're using materials which are already readily available, which kind of means that in the larger scope of an industrial setting, the process will be more easy and cheaper to make. And then cancer therapeutics. Obviously, the number one thing with any type of cancer therapy is that we want it to be able to kill cancer and save patients. So cancer as a disease and as a field. So 12 million Americans have a history of cancer, and there are 2 million new cases diagnosed each year, with 1 million of those expected to die. So with a 49% survival rate, cancer is one of the most prevalent issues and diseases facing our society to date. And a lot of people ask, why hasn't a cure been found? Well, there are a lot of targeted treatments that are out there, but they prove to be very cost ineffective and they're not easily accessible by many patients. So a cost-effective targeted cancer treatment is within reach, and such an approach is made possible through the use of nanomedicine. So what is nanomedicine? Nanomedicine is the development and application of nanoparticles for biomedical purposes, and these nanostructures typically range from 5 to 100 nanometers in size, and they have a lot of promising use in both diagnostics and therapeutics. And recent nanomedicine approaches for facilitated molecular imaging, targeted drug delivery, and various diseases and disorders have been proving very effective in clinical trials. Alright, so purpose of study. So current cancer therapies have many side effects, and this is due to the systemic exposure of drug. Now what this means is that instead of targeting cancer specifically, you're instead injecting large amounts of toxins into the body and into the bloodstream. And I attribute this to a similar fashion as if you want to find a needle in a haystack, well, why not just burn the haystack? And it's not a very effective approach. It leads to the burning of the entire haystack. It leads to side effects and all of the things which cancer treatments are currently infamous for. So in targeted therapies, which I'm working with, this allows for a lower dosage than with non-specific ones such as chemo. And this decrease in side effects also is attributed with an increase in cost efficiency due to the utilization of cost-effective materials. So goals and hypotheses. So I want to locate, target, destroy, and image tumors. So how do I do this? Well, using the stealth avoidance of immune system, we kind of allow these nanoparticles to go throughout the body's bloodstream and throughout the body system without being detected by the immune system, which allows for a longer circulation time and a longer time to be able to find the cancer site. And this targeting is done through the EPR effect, or the enhanced permeability and retention effect, which I'll get into a little bit in the next slide. Also, once these nanoparticles reach the cancer site, I want to be able to induce apoptosis. And apoptosis is the process of natural cell suicide. So as opposed to chemo-based treatment options, which poisons the cancer cells to kill them, we're instead using a more natural process that the body already has installed to shut down cells which have kind of gone out of control. Also, I wanted to include a component which allows for the imaging during and after the treatment, which kind of gives an interesting sight into what's happening as well as a confirmation of the treatment. Alright, so methods of targeted therapy, and essentially I'm going to break down the enhanced permeability and retention effect. So a tumor is constantly dividing and growing exponentially, and that's why tumors can grow so fast. So in order for a tumor to grow so fast, it needs to gain much more nutrients from the bloodstream. And also, as it's gaining these nutrients, that means that healthy cells aren't getting these nutrients, which contributes to the lethality and the danger of the disease. So in response to needing more nutrients, tumors excrete various growth factors, including the vascular endothelial growth factor, to allow for the growth of new, as well as more growth on top of current blood vessels. So this results in an angiogenic expansion of the tumor vasculature. It's more complicated, it's more interconnected, but also these immature vessels are morphologically strange, which allows for the slipstreaming of nanoparticles right into the cancer cell, essentially a direct highway right to the cancer cell. So this describes the enhanced permeability and retention effect, and this allows for tumor targeting for nanoparticles, at least for it to get to cancer sites. Okay, so the self-assembly of nanoparticle, and this is one of the factors that's leading to the cost reduction because of this process. So phospholipids, or block copolymers, which are the two different amphiphilic materials which I'm using, both have these amphiphilic properties. And essentially what a molecule needs to be in order for it to be amphiphilic is that it has both a hydrophobic and hydrophilic part. Now what that means is that hydrophobic things hate water and will do anything to escape it, while hydrophilic things love water and will expand into it. They love aqueous environments. So then these amphiphilic molecules, when put into an aqueous environment, can self-aggregate into these nanoparticle structures. And within these nanoparticle structures, if you include a hydrophobic or water-hating material, such as a drug or an imaging part or a polymeric core, this will allow for the kind of wrapping of these cores into this nanoparticle, which then is just as comfortable floating through the bloodstream as it is in a test tube. Alright, so the design and synthesis of these two nanoparticle formulations which I've been working on. So in the synthesis process, the first thing we're going to do is we're going to load one syringe with the nanocarrier materials. So what this includes is the staurosporine, or the cancer-killing drug, the imaging agent, the amphiphilic polymers, the lipids, etc., as well as we'll fill 2 syringes with water. So what we put these into is what's called a microfluidics chip. And they look like these, and essentially it's a tri-channel system. So in the centermost and top part, you're putting in your nanocarrier or hydrophobic and amphiphilic materials, so everything which is going to end up being the nanoparticle. Then on either side, we include water. And since we have things in the nanocarrier solution which hate water, when they're introduced to the 2 water channels on either side, down in this microvortex which forms, they will self-aggregate into these nanoparticles. So we begin pumping the syringe contents into the microfluidics chip, as well as by altering the rate and volume at which these syringes are pumped, we change the stability, the size, as well as the characteristics of the nanoparticle. And so it was with tinkering of these kind of flow rates that I was able to find the most stable formulations. So the first thing that kind of happens is there's the formation of the hydrophobic core. Now for the block copolymer, it has block copolymer amphiphilic materials, which is kind of the more modern and new approach to nanomedicine. And then for the lipid micelle formulation, it's simply phospholipids as well as the staurosporine within. Then these nanoparticles are wrapped by either the block copolymer, which is the PEG and block copolymer amphiphilic coating, or the phospholipid coating. The last step is purification by viviflow centrifugation, and when these nanoparticles come out of the output of the chip, since they've been introduced to so much water, they're very dilute. So then we have to centrifuge them in order to get all of the liquid out, as well as introducing new types of liquid depending on what we want to suspend the nanoparticles in. So the research design and results. So first we have to check the size, and we do this by using a Zeta-PALS scanner, which is scanning for 3 things: the polydispersity, which is the uniformity of the solution and the nanoparticles within, the average size. Then we're also doing transmission electron tomography to get actual images of what the nanoparticles look like. So here you see the data that shows that they're all within the 5 to 100 nanometer range, which is for the enhanced permeability and retention effect, so in theory these should be able to reach cancer sites. Here you see what the block copolymer nanoparticles look like under a TEM microscope. Then you see what the lipid micelle molecules look like. So next thing to check is the composition. So the drug incorporation is tested by comparing the free drug, which is just staurosporine, non-purified particles, so the stuff which just comes out of the output of the microfluidics chip, which has all of the water, all of the solvents and everything, as well as the purified particles to a specific wavelength of staurosporine in high-performance liquid chromatography, which allows for us to see exactly how much of the staurosporine we included and exactly how much ended up in the nanoparticles. This is important because when you're prepping a dosage for a patient, you need to know exactly how much of the drug is included within each nanoparticle, or at least within each batch and sample of nanoparticles. So in order to test this and find this out, first we created a concentration curve so we could see exactly how much and compare it to previous set models and concentrations of staurosporine, and then we were able to see the staurosporine incorporation. So for the block copolymer formulation, while there was less staurosporine included, it would still be enough to be effectively toxic for the cancer cell, while in the lipid micelle formulation, an extremely high amount of the staurosporine was included within the nanoparticles. So the next thing I checked for is stability, as these nanoparticles are useless if they're not able to be stored for long periods of time, as well as to be stable within the body that they're introduced to. So I checked it at two temperatures, the stability, at 4 degrees Celsius, which is that of a freezer, and then at 37 degrees Celsius, which is the body temperature, as well as the temperature of the liquid passing through the bloodstream. So the stability was then measured by normalizing the data, which I collected for 2 weeks using that same ZetaPals scanner method which was talked about in the size. So as you see, for long periods of time, these are very, very stable particles, and I would have been able to prolong this experiment if there had been less evaporation of the solvents. So these things can really be stored and can circulate in the body for a long time. So next I checked drug release profiling. I wanted to see how much drug was in the nanoparticles to start with, as well as how long it took for the drug to be released without being taken up by the cancer cells. So this is simply how much of the staurosporine will accidentally leak out during the process of circulation. So for both of these, they showed that they have very desirable release patterns. So the block copolymer approach seems to resemble a burst pattern of release, which means that a large amount of the drug is released naturally throughout the process of circulation. So hopefully, the nanoparticles will be able to reach the cancer site before the 3 to 5 hour range, which would allow for a large amount of the drug to be released into the cancer cluster, effectively killing a lot of cancer cells. Now this is good because if these nanoparticles are able to reach the cancer site within 3 to 5 hours, this means that the nanoparticles which are not taken in by the cancer cells will actually release drug in the surrounding area, which are still cancerous, they're just not taking them in, so it allows for kind of total wiping of the tumor. For the lipid micelle, it seems that the pattern of release is much more gradual and slow, and if I had extended this experiment over multiple days, according to the current pattern, it would seem that these nanoparticles are able to hold on to a lot of their staurosporine for multiple days. So next up is the in vitro cytotoxicity analysis. So what I wanted to see is that in a petri dish, when cancer cells come in contact with my 2 nanoparticle formulations, how much will they kill, and will anything be killed at all? So the results showed that the empty lipid micelle nanoparticles and block copolymer nanoparticles, which have no drug in them at all, which I made specifically for this test, are almost showing that no cancer cells are killed. Now this is great because it means that inherently the materials which are being used in the nanoparticle do not on their own kill cancer, and this is great because after the drug is released within and the whole process of therapy is done, we want to know what happens to the molecules which are left over, and this shows that they're not harmful to cells. So that's great to hear. So then the staurosporine-loaded lipid micelles, as concentration increases, they're showing a very significant killing ability on both of these formulations for cancer cells. Now what's great is the block copolymer approach shows that even with very low concentrations of the nanoparticles, they're still killing a significant amount of cells and wiping the dishes out. So this means that after 1 or 2 or maybe 3 treatments, this could have a very, very good chance of getting all of the tumor. And the last was the in vitro endocytosis confirmation. So I wanted to see how the actual nanoparticle and the cancer cell was interacting. So I included some fluorescent dyes within the nanoparticle and looked at them under a fluorescent microscope. And in this image, the top 3 images are only for the lipid micelle approach. So the first thing that you see is nanoparticles, as well as the cell morphology of the actual cells. In the one slide over, you see only the cell morphology, and in the slide after that, only the nanoparticles. So as you see, most of the nanoparticles actually found their way within the cancer cell, which is great to hear. Now on the bottom, which is the block copolymer, you see that same pattern. So the first is a superimposition of the 2 different images. So the second one you see is the cell morphology, and the last one you see is the uptake of the nanoparticles. So now here what's really great is that rhodamine dye, which is what you see in pink, which I included in the lipid micelle formulation, is actually the fat directly conjugated to the rhodamine dye. So the fact that you're seeing pink here means that that's attached directly to lipids. So this really proves the stealth ability of these nanoparticles, because the cancer cells are recognizing the materials of the nanoparticle as their own, as things which they can use, certainly not nanoparticles that have come to kill you. And as they kind of take in the nanoparticle as their own, it's then facilitating the process of apoptosis and killing the cells. So the conclusions and discussion, the results of this study. So the nanoparticle materials were easily purchased as they're fats and polymers, and only a few of them need to be specially made, with the exception of staurosporine. And staurosporine we had to get custom made due to the non-use of it in current scientific research, and therefore it had to be specially produced just for us. But in terms of a future, more industrialized setting where this drug is actually used in a therapy in this nanoparticle, it would be a much easier process to obtain. Then the 2-hour synthesis and less than 2-day characterization process, which is necessary for the actual determination of a treatment dosage, proved that it wasn't a very intense process and that it could be replicated a lot of times in an industrial and pharmaceutical setting. Then the stealth ability of these nanoparticles, where it avoids interaction with the immune system and the mononuclear phagocyte system, shows that the nanoparticle approach really allows for drugs to be delivered directly to cancer cells without triggering the body's natural immune responses to foreign objects. Staurosporine is also toxic to all cells, but the enhanced permeability and retention effect allows for the delivery of this to cancer cells only, leaving healthy cells healthy. Then the study also reveals that these nanoparticle formulations have the potential to be used for a targeted tumor treatment to treat cancer, and these nanoparticle characteristics and compelling in vitro data which I have obtained justifies a future in vivo study to determine the pharmacokinetic and therapeutic value of this as a cancer treatment. So the future studies. So my age, since I am under the age of 18, did not allow me to utilize animal studies with New York State law. And therefore, I would love to be able to do a collaboration with an undergraduate institution biotech lab in the future to perform the in vivo mouse model studies. Also, I'd love to be able to include something for the study of tracking nanoparticle distribution as the nanoparticles circulate throughout the body, as well as a new method for the confirmation of treatment limitations in solid cancerous masses which they'd be used for. So I want to see, really the limitations of these nanoparticles are. As well as the future in vivo studies, I'd really love to be able to get very definitive data on tumor profiling and the shrinkage, as well as the treatment timing which is required to effectively kill cancer. Alright, so special thanks to my mentor, Dr. Willem Mulder, unbelievable guy who took me under his wing, just some kid with an idea and a train ticket, and gave me access to $1 billion lab. Unbelievable. Then as well as Francois Fay and Brenda Sanchez, who were my parents throughout this whole project and taught me everything I needed to know, never holding my hand but teaching me how real science is done. As well as the Translational and Molecular Imaging Institute, where I conducted my research. Thank you so much for opening up your lab to me. The NIH Program of Excellence in Nanotechnology for allowing me to use some of the lab's funding, as well as Dr. Rogers and the Hendrik Hudson Science Research Team back in my hometown. And references and works cited, special thanks to everyone in the field who has contributed previous research and allowed future research to take place. Thank you so much for watching, and I hope this has been an informative view into this cutting-edge type of research which will hopefully allow us to eradicate cancer from the world for all future generations to come.